Greetings, students. Mr. Allen here. Today we're going to continue our discussion about finding limits. Specifically, we are going to look at evaluating limits analytically. This is basically, so up to this point, you've done them graphically and numerically, and we've talked about estimating those. So analytically would be if you're trying to find a limit using rules and properties and steps and not just trying to guesstimate it using your calculator or a graph. So this is actually more ideal in terms of the way a mathematical or a math person would want to try to find limits. So our objectives here are to find limits using properties, develop strategies for finding limits, evaluate limits using the dividing out technique and the rationalizing technique. So the first slide here is talking about something that I've already mentioned in our previous lesson, which was on the direct substitution. Ideally, in almost all cases in real life, but in this class, not necessarily, you can do the limit just by doing direct substitution. So for example, if I told you that the function was y equals x squared, and then I said, find that limit as x goes to 2, well, the answer is 4, because x squared is a continuous function that we can just plug any value in and we get all the values out pretty much positive. Anyways, however, we're going to look at some properties that are going to help us wiggle our way around some issues if we have them. I'm not going to go through each of these, but for example, this first property right here basically says the following. If I want to know the limit as x goes to some value c of, let's say, the constant function, 7. That's what b is. B is a real number. It is a constant. Well, guess what that limit's going to be? No matter what c is, well, it's going to be 7. And that should make sense. If you think about the graph of y equals 7, what will the output always be? What will the y value always be? It will be 7. Here we have an x, so this one is variable. So it's just going to be equal to c, and then we've got one for an exponent. Here are some more properties. I'm going to kind of highlight some of them. You need to look through all of them. They are all very useful. So some difference. So for example, if I'm trying to find the limit of a function, let's say plus another function, doing plus only, then it's just going to be the limit of the first one, L, plus the limit of the second one, K. No big surprise there. The limit of a product is the product of their limits. Again, no big deal. These properties are very important and helpful, and we're going to see these properties throughout the year in various aspects of this class. So I'm not going to work this one out by hand. I'm going to basically I already have it typed in here just to speed up this process because I'm trying to limit the video to 10 minutes. So let's say I had this limit, and I'm asked to find it analytically using properties. So how could I do that? Well, the first thing that I could do is I could break, since that addition's there, I could use the addition property. This is property number 2. So I took the 4x squared plus 3 and I split it into the limit of 4x squared plus the limit of 3. And I could use property 1, which is the scalar multiple property. So instead of it being just 4x squared, I can pull the 4 out in front. So it becomes 4 times the quantity of the limit x squared plus the limit of 3. Then I could use limits 1 and 3. So now what I can do is I can basically plug this 2 in for the x, and we're going to do x squared plus 3, and of course we get the answer of 19. Now you might be thinking, wait a minute, Mr. Allen, couldn't I have just plugged this 2 in here in the first place and got the answer of 19? The answer is yes, you could have. Direct substitution in most cases is what you would do. But in this class, there's a lot of times when on quizzes and tests and homework, that's not going to be the case. But you always want to try direct substitution first. Here's a theorem about the limits of polynomials and rational functions. And it basically says that if this is actually, here's what it's saying. It's saying if the limit of the p function is p of c, in other words, we can do direct substitution. Then if we have a rational function, where again we've got this p of x function, divided by q of x, we just need to make sure that q of c does not equal 0. So in other words, if it's not being divided by 0, then you can simply use the quotient rule. I'm I'm going to kind of skip this one. This one involves radicals. Just remember that whenever you're doing a radical, the stuff under the radical is not going to be a negative number. And I guess I should probably state that. In this class, we are only interested in real numbers. Limits of composite functions, so that's composition. It's basically what you think it is. This is probably the most important slide in all of the rules for limits. This says a function that agrees at all but one point. Now, I'm going to actually skip this theorem and come back to it. I want to show you an example I think that will make sense. Consider this function here. This is the f of x function. It's a piecewise defined function. We are given that the first piece, when x is not equal to 1, it's going to be this graph right here, x squared plus x plus 1, which is going to be a parabola. When x is equal to 1, it's just going to be 1. Now, what I'm going to do is I'm going to show you the graph of that function. This is the graph of this function. So my question is, what is the limit of f of x? That's the limit of f of x. My handwriting there is horrible. As x goes to 1. What is that limit? Well, look at the picture. When we look at the picture, we can easily see what that answer is. At least I think you can. What would be the predicted x or the predicted y value as x goes to 1? Now I'm going to go back to the previous slide. What this theorem is saying is if you have a function that is nearly identical to another function, it's identical in every way except for at one point, then you can use the function that helps you get the limit. So what I'm saying is this function is equivalent to this function. If I were to just draw this function, not the piecewise defined, where that hole is filled in by this curve. So let's pretend that this part doesn't exist in this function. So in other words, I can just go ahead and evaluate this limit using the g function. The g function and the f function are not the same function. The g function, which would be that parabola x squared plus x plus 1, is not the same thing as this piecewise defined function up here. They are the same except for at the point when x is equal to 1. Since that's the case, I can use the g function to find that limit of 3. You'll see some examples of this on the homework. Okay, and you'll see it actually in this example here when we divide out technique. So if I plug in, if I do a direct substitution now with -3, I'm going to kind of speed this up, but if I do a direct substitution here, you are going to end up with 0 over 0. That is a problem. But we have some good news. If I factor the numerator, x squared plus x minus 6, that is equivalent to x plus 3 times the quantity x minus 2. And then, of course, the denominator is x plus 3. So if I divide this by x plus 3, then I've got this as x plus 3. Those guys are going to cancel out. So what I'm telling you is that the function, oops, this should be a y, sorry. The function y equals x minus 2 is equivalent to this function, except at the point x equals -3. But that means I can use this function to find my limit. So I'm really just interested in the limit as x goes to -3 of x minus 2, which is clearly -5. The answer here is -5. Now notice I didn't use a graph, and I didn't use my graphing calculator to help me get that. So here's graphically, if you were to graph this in your graphing calculator, you'll see that the graph of this function looks like a line. It actually looks like the line y equals x minus 2, but you'll see that there's a hole right there when x is equal to -3. Now note, this function and this function agree at all but one point. Okay, so we're about 9 minutes here, so we're going to get the last thing done, and this is rationalizing. I'm going to just basically tell you this. I'm going to just do this example. You guys have heard of rationalizing the denominator. We're going to actually rationalize the numerator. So if, by the way, if you plugged in 0 here, you're going to get 1 minus 1 over 0, which is 0 over 0, right? So again, you're stuck. All right. So what we're going to do is we're actually going to get rid of all this stuff. We're going to rationalize the denominator or the numerator. So what I'm going to do is I'm going to multiply by the conjugate of the numerator, which is the square root of x plus 1 plus 1. And I've got to do the same thing on the bottom, right? So whatever I multiply on the top, I'm going to multiply by the bottom. So this is going to give me the limit as x goes to 0. Now, when you foil the numerator, you're going to get the quantity x plus 1, and then you're going to get minus 1 on the top. And on the bottom, you're going to get x times the quantity, the square root of x plus 1 plus 1. This is a plus 1. Okay, I'm not sure why that slash happened there. Now, guess what happens to the x plus 1 minus 1 on the top? Well, that's going to give us the limit as x goes to 0 of x over x times the square root of x plus 1 plus 1. Now, don't distribute this x yet. Now we can go ahead and do direct substitution. So that's going to give us 0. Oops, I've got to cancel something though first. Let me cancel that. Sorry, I know I'm getting over time here. Those can cancel, right? So this last step is going to be the limit as x goes to 0 of 1 over the square root of x plus 1 plus 1, which is, of course, going to give us 1/2 when you do direct substitution. You're going to do direct substitution. Now, I need to stop there because we're at 11 minutes. You can check this answer with your calculator. And actually, I've got a picture right here. Here's the graph. And you can see that there's this hole right there. And you can look at this table to verify that the answer there is 1/2. Sorry, I went a little bit long there. There's Mr. Miller.
Messages for seniors. This is for seniors, so the last name.